My name is Chris Wichern. Welcome now to my second participation in Mahr's Surface webinar series. Today I'm going to be talking a little bit about 2D versus 3D, or profile versus aerial surface analysis. If you attended my last webinar, I talked a little bit about the new products, so the products themselves that are part of our new MarSurf 3D product line. I also talked about some of the applications of these products. Today we're going to get a little more academic, a little more mathematical, and we're going to talk about what are some of the differences, why we have these two different product lines, and how we kind of choose between them, and what some of the differences are with the new tools. So, as I started out the last presentation, I kind of like to set the context for what we're talking about and where it is in the big picture of dimensional metrology and dimensional metrology at Mahr. So my field is this tiny little field, surface metrology, amongst a large sea of tasks, of length measurement tasks that we do at Mahr. It's surface metrology, probably better termed dimensional surface metrology. So it's one of many tasks that we do at Mahr, but even amongst this subset at Mahr, dimensional surface metrology, we have a lot to offer. We have our MarSurf product line, which is our tactile instruments. These instruments use a diamond tip stylus to trace across the surface to produce a cross section of height as a function of position, which we in turn use to calculate and produce roughness parameters. We offer that in a pretty wide range of products, from the PS10, which is a very easy to use handheld product, press the green button, get roughness, all the way to the MarSurf CNC instruments, which are multi-axis automated CNC tools for more complex analysis tasks as well as more complex parts. My product line are optical instruments. It's the MarSurf 3D product line. And even inside of this product line, we have a pretty wide range of products, everything from interference microscopes to a handheld confocal microscope, a portable confocal microscope, up through larger CNC tools, multi-axis CNC tools using either a microscope or a point sensor or a line sensor. So we have, in this subset of dimensional surface metrology at Mahr, we have a very large range of tools that we can use. That said, even amongst this big range of tools, there's one task that is done by all of these tools. All of these tools do surface finish measurement. Some of the tools do other tasks as well, but one thing that they all do is surface finish measurement, which kind of begs the question, well, how do we know which one? Why do we have this? What's the point? Well, there are reasons that, there are times when we want to use a skidded stylus versus a skidless stylus on the tactile side, on the MarSurf side. On the MarSurf 3D side, we have applications where we need to use a point sensor or want to use a point sensor versus a microscope, or a microscope is better than a line sensor because it's more optimal for that task. At the same time, we need to compare the two different techniques. So when do we use a tactile tool versus when do we use an optical tool? And that's a big discussion, but that discussion it's not really so much about the instrument. It is also about the instrument, but today we're going to discuss that from the perspective of the analysis. What are we doing with the data that we get out of that tool? We're going to look specifically at that and how that affects our decisions in terms of which tool we use and how we use those tools. So this is where I was when I realized you all weren't hearing me, so we're caught up again here for the most part. Talk about the two different types of analysis that are listed in the title of the presentation here. So profile measurements, also known as 2D or linear measurements on the one side, aerial measurements, also known as 3D measurements or 3D roughness, or however you want to phrase it, on the other side. Those are the two topics we're going to be kind of talking about today. On the profile side, these measurements are, we get guidelines for these measurements from ISO in the form of 4287 and 4288, and ASME in the B46.1 standard. What we're really doing in this is, if we look at the graphic that I have in the upper right, it's a 3D graphic But if you look at that 3D graphic, you will see a west to east black line. That's the black profile. That's the type of data that we are analyzing when we're talking about profile measurements. It's a single or maybe 3 or 4 or 5 profiles along a surface that we are using to describe that surface. This technique, these profile measurements are very, very well suited for well understood processes, well understood machining technologies. And what I mean by that in the concrete context is we know a process is stable, a process is well suited for profile measurements when we know we can monitor that RA value. We can look at our RA value and say, oh, RA is climbing, it must mean we have some tool wear, time to replace some tooling, or RA is climbing up, our feed rate must be off, or RA is dropping, the laser must be too hot on the welder, or RA is climbing again. So these very simple things, we can look at RA and we know exactly, from our experience, our 50 years of experience with this process, our 100 years of experience with this process, we know when RA does that, we need to go look at this. Well understood process. These profile measurements are great for that. Profile measurements, we can get them from either tactile tools or optical tools. I think the idea that they come from tactile tools is quite obvious, but from the optical tools as well, we can either use a point sensor to generate a profile directly, or as you're seeing in the graphic on the upper right, we can take a 3D data set and we can extract a profile from it. We can break it down to a single or multiple profiles. So we can get to this profile measurement analysis either way. The one thing that we can't do with these profiles, we can't do it very well, can't do it very effectively or efficiently, is we can't really measure complex surface structures. And for that, we have our 3D. That's our jumping off point into 3D. The 3D or the aerial measurements our guidelines for those come from ISO 25178 and the new ASME B46.1 that specifically deals with 3D parameters or aerial parameters. As we've said, ideally suited for complex surfaces. Generally, these days, 99% of the time, 95% of the time, when we're talking about aerial measurements, 3D measurements, we're talking about optical tools. Yes, we can do it with contact stylized-based tools, absolutely. Probably not as fast, or effective, or efficient, but there absolutely are applications where we do that and where it's necessary. What we can do with these tools, and this is the important thing here, is we can do some targeted characterization of our surfaces based on what we expect their in-service performance to be. So we can look at that part or that surface, how we expect it to perform when it's part of a mechanism, when it's part of a machine, when it's a consumer product. We have some performance expectations. The 3D parameters allow us to potentially identify the mechanism that connects that in-service performance back to an actual parameter. We can always, even with 2D parameters, we can always see a link between, or there's no sense in measuring it, we can see some link between the parameter and the in-service performance, but we may not necessarily have a mechanism for that or an understanding of that mechanism. The 3D parameter can provide us, the 3D parameters can provide us with that insight, with that additional knowledge. Back to 2D quickly, put a couple more conditions, a couple more requirements on 2D measurements. And you'll understand in a couple of slides why I'm doing this. Some guidelines / requirements for doing 2D profile measurements set by ISO or ASME are, we really need to have enough measurement length. And ISO controls that by talking about our evaluation length, they refer to it, and they set for different RA or RZ values or RSM values, they set different filter sizes, different cutoff lengths that we're supposed to use. That topic is an absolute rabbit hole. There's some mixed understanding of it, some people who don't necessarily agree, and there's great reasons not to. That's enough for a 10-part webinar series. We're not going there very much today. But the point being, there's a length requirement for these. You have to have a minimum length. The other important requirement when doing these 2D profile measurements is generally the guideline is measurement has to be perpendicular to the lay of the surface. Again, in my example here, the lay of my surface, that's a diamond turn surface, my lay of my surface is north to south along the machine to tool marks, my measurement direction has to be perpendicular to that. So it has to be west to east. That's a guideline set for these two, or provided for these types of measurements by both ISO and ASME. And we talked earlier about the third bullet point, and that's, it should be a well understood process. You should know the relationship between RA and what the condition of your product or your process is. So those are kind of the conditions, guidelines for using 2D. But then we have 3D, and let's talk a little bit about 3D. 3D data and how it's presented to us comes in many different forms. What we can do with it, there's a lot of different things we can do with it. In its most fundamental form, we're talking about the microscope in this case. Because it best represents the 3D data. So we're going to talk about microscopic data. A single measurement area, we call it a field of view, and FOV for short. It's usually square or rectangle. For a 20x lens, for example, it's about 0.8 millimeters by 0.8 millimeters. We can in that small area, we can already start doing some surface analysis, some surface roughness measurements. However, sometimes, just as ISO provides guidelines for profile measurements, ISO also provides some size guidelines for 3D measurements. They're a little more flexible, but they do provide them in cases where we need to increase our measurement area. We can do what's called stitching. So we can tell the tool to automatically acquire multiple fields of view as necessary and combine those back together automatically to increase that area, the total measurement area. Other things, I guess it's implied, but I should make it explicit. The data coming out of these tools, it's digital data. That means we have that data set. We can save it on our PCs. We can save it on our laptops. We can open it in different software packages. We can save it, come back to it in 3 months, come back to it in 3 hours, and change our mind about how we want to analyze. And it's very flexible. And what I'm showing here is we can take a 3D data set and we can do a single profile, or we can do a profile series. So instead of taking one west to east profile to measure roughness, I can take 1,000 of them. I have enough room in that data set for 1,000 west to east profiles to measure roughness. I can look at the data like that. If for some reason, some functional reason, I wanted to do a circular profile, I can do a circular profile if it fits better. So it's digital data coming out of these tools. It allows us a bit more flexibility, is the point here. The final point, this is a big slide, but really the only thing we're interested in is actually down here at the bottom. We're comparing a tactile measurement data to optical or 3D, so 2D data to 3D data. Basically put, when you're doing a single profile trace with something like a PS10, measurement time is about 11 seconds, and you're getting, somebody did the calculation, 11,200 data points in a typical trace. On the confocal microscope side, which is what these measurements are from, a single field of view, so that one square field of view is 1.4 million data points. So the point of this slide is to say the nice thing about aerial data and this digital data is we have a lot higher data density. So at that point, I'm going to put up the stop sign and let's take a second. And why are we having this discussion? Why are we talking about this? What's the point, Chris? And there's 4 points, really. As it says there, for decades, we have been measuring roughness using profiles, and it has worked great. Why? For more than decades, practically a century at this point, right? We've been doing this. Why change now? Well, there have been a lot of manufacturing advances in our both subtractive and additive manufacturing have made some big changes. So we see many, many more non-uniform, non-isotropic functional surfaces that are designed to be non-uniform, to have very specific features on them. And a single profile trace isn't enough for that, or it may not capture that completely. That's the biggest reason. It's a big reason, but we'll look at some details of that. Related to that, but slightly different, is we can, this is where I was talking about a little bit about mechanisms. We can, with the 3D, we can target our analyses, we can target our how we assess the surfaces to look at specific in-service performance and how we can best characterize that. So we really have, looking at these complex structures, how do they perform in service, and how can we measure dimensions, information that talks to how they perform in service. And then finally, or not finally, excuse me, the third point, sometimes we have these very, very, very small parts now that we need to look at, and sometimes there's not enough, they're just simply not big enough to really adhere to the ISO guidelines. And I'll talk about why that's important, even though it's just guidelines, why those guidelines are important, why they're in place. I'll talk about that and how we can logically use 3D to get around that issue. And then finally, this is a pretty big topic too, and this is a 20-part webinar series, quite frankly. But the ISO 25178 gives us many, many sophisticated parameters, and I'm going to do my best to get through not all of them, but the groupings of them for you today, just to get your feet wet a little bit there. So, and jump right into the first one: non-uniformity, non-isotropy of modern surfaces. So this is a very basic diagram to explain what I'm talking about here. The profile on the right could be attained from both of those two surfaces that I show, from both surface A and surface B. If we're doing a profile, we could see that profile from both surfaces. That profile would indicate to us that surface A and surface B are the same. Obviously, surface A and surface B are absolutely not the same. They are going to behave functionally very, very different. But if we were to measure the RA at that, I'm kind of cherry picking the location for surface B. It may not be realistic, but nonetheless, it could happen that we have this. Even if we chose a different location on surface B, the other option on surface B is the flat area, and we get a very, very flat surface, which does not represent that surface. So the point stands that a profile, while it represents surface A very, very well, and surface A looks very much like a ground surface or a rolled surface or an extruded surface, these are the surfaces that we traditionally say make your measurement perpendicular to the lay and everything's great. And it really is. It does do a good job of defining surface A. It does a terrible job of defining surface B. So this is what we're talking about with these non-uniform, non-isotropic surfaces. Here is a little more real example of that. And in this case, we have a surface that has a couple of different things going on. We have some machine marks. Those are those grooves we can see running north to south on the screen. But we also have these pocks, or these pores, these indents on the surface as well. So we have two different processes at least have happened to this surface. And we may need to determine which of those effects are in service, which effects are we can use them to either monitor our manufacturing side, or we can control them to improve our performance side once it goes out to its application. So we have a couple of different things, but either way, we need to potentially be able to distinguish one from the other. A profile, you're not going to be able to distinguish one from the other. You may say, looking at those green profiles on the right, oh, well, Chris, actually it's obvious where the pores are and where the grind marks are looking at that. Well, I'd counter with saying it's obvious where the pores are versus the grind marks, because you can see where they are on the image on the left, and you associate that when you look at the image on the right. If you just had one of those profiles and nothing else, you would have no idea what's a pore and what's a valley, really. Or you might be able to guess, make some educated guesses, but you wouldn't have much to stand on. So in this case, even though when making those profiles, we can absolutely adhere to ISO 48287 to the letter, we can do it. But the problem is because we can't really, we can't quite determine whether we're looking at grind marks or pores or which we want to do. It's not optimal. I talk a little bit about the tolerances and the ranges there, but that's another discussion. We'll kind of skip that for now. The point here is that we can't distinguish pores from grind marks, but we can do that later. Another little more easy to grasp, or easier to not so much grasp as for me to explain to you, is if we look at a honed surface. So on the left, it's obviously a 3D measurement of a honed surface, but on the left, I'm showing what happens if we do profile measurements on that honed surface. If we measure from southwest to northeast, so down here, when we do this measurement and we cross one of those hone marks, we get a fairly large RA value. We're going to get a pretty big RA value. in the case of this measurement, where we intentionally tried to get down inside a hone mark, it looks rougher, but that's because the scale is different. The RA value is actually much smaller. So depending on where we place our traces in surfaces like this, I understand that for an internal combustion engine where this is probably from, there are very specific guidelines. But in general, looking at a surface like this, depending on which direction we do our trace, there's going to be a big effect on the RA. And we may miss important features, or we may catch features that we don't want to. The big advantage to aerial, specifically for surfaces like this, is we can force ourselves to catch all of the data. That SA parameter, that represents all of the hone marks, all of the, even the pits that are in the surface. Again, there's another webinar there. If Mark Malberg were here, he would probably have some words for me on this topic. But the idea is if we can use this SA to capture all of the data in that surface that represents our roughness. So that's a big point here. We have a non-uniform surface, a non-isotropic surface that is going to give us issues when we're dealing with profile measurements. We're going to have big changes depending on where and how we align our profiles. On the SA side, over here on the aerial side, we're using all of the data available to create a single number to represent that surface. It captures all of the information on that surface. There's more to that topic, of course, but that's a good introduction to it. Next up, let's take a look at some more complex characterization of some more complex surfaces. And here we are back to this surface. Like I said, I'm going to get a lot of mileage out of this measurement today. Again, we've got our machining marks, grooves, and we've got these pores. At the bottom here, I have some profiles that we've done just across the machining marks and just across the pores to kind of give you an idea of what the structural difference is of these. The idea, we would want to quantify those machining structures on the left-hand side one way. RA, RZ will work fine for those. But on the porosity side, that's really not, those don't help us very much. We need something else to quantify those pores. So two things are happening here to be quite clear. The porosity, those indents, they need to be quantified somehow differently outside of ISO 4287. And in order to quantify the machining structures according to ISO 4287, we need to get rid of the pores. So there's two different topics here in terms of this complex structure. So there's two tasks that we have, and I'm going to do those two tasks on this slide. So on the left-hand side, we're going to start out over here. We have our as measured surface. So this is the surface we have been looking for. The first task that I do is I am going to isolate and analyze these pores. So I can tell the software, go in, and we have a couple of different algorithms that we can use. And my apologies for the German language on my graphic here, but we used essentially a height thresholding technique to isolate these pores. And what the software has gone through, it has assigned a number to each one of these low spots, these dents or pores, and it has gone through, and in this case, they've calculated the maximum height of each of those pores relative to the mean plane. And it's showing the result for one of those pores. It refers to a particle, but it means that pore. So it's a 4 micron deep. We can do that for each of the pores or each of these depressions individually or as a whole, and we can also collect the statistics on them. More than just the depth of that pore, we can also calculate the volume of that pore, the mean radius, the circumference, the aspect ratio, etc., of each of those pores, as well as the statistics on those parameters for all of those pores. So we are able to, because this is digital data, because it is 3D data, we're able to treat that depression, that pore, in its actual shape and give parameters that are related back to that shape. The other half of this task is, well, we want to look at the grinding marks without those pores. So here we've simply taken the result of this subtraction and we've left behind just the grinding marks. And now we can go in and we can look at just the fundamental roughness. And in this case, we've chosen SQ. For some of you, SQ may be a new parameter. For some of you not. But that is very similar to the ISO 4287 RQ. That is the root mean squared, the RMS roughness. The difference here being it's not the RMS roughness from a single profile, it's the RMS roughness from all of the data in this surface. I also show SAL here, which we'll talk about the mathematics behind that in a minute or two. But S10Z being the 10 max min point sets. So similar to RZ, perhaps a little more robust. Other things we can do with this structure on the right-hand side, we can quantify, we can start to quantify the isotropy of this structure. I know isotropy was the previous topic, but here I'm showing how we calculate that. This surface is a very anisotropic surface, so we're showing a very low isotropy value. Isotropy runs from 0% to 100%. Isotropy means if you were standing in the middle of that surface and you took a look at 360 degrees, how well could you distinguish which direction you were looking at? Would you know if you were looking at 90 degrees versus 0 degrees, or if you're looking north versus east? 100% isotropy means you would have no idea which direction you're looking at, or your surface has no lay. Very low isotropy numbers indicate that your surface has lay. These are things that we can calculate in a single measurement using these 3D parameters. Third topic for this is when we have very, very small surfaces, how do we deal with that? And we can use our 3D surface metrology to deal with those very, very small surfaces. So let's take a look at an example when that might be important. The drawing that I have here, my little sketch down there, that's supposed to represent a shaft with a groove, with a groove for a seal on it, or a groove for an O-ring on it. And I'm proposing to you the case where we have a drawing of that shaft with a call out for the bottom of that groove of RZ of 6.3 microns. We know for an RZ of that size, that ISO is going to give us the guideline that we need a cutoff of 0.8 millimeters, and which also tells us that we need a minimum strike length to adhere to that guideline of 0.8 millimeters, absolute minimum we can use. And actually, for a stylus tool, we need even more than that physically. We obviously can't do that because if we look at my little sketch down here, it's 0.5 millimeters, so it's a half a millimeter wide. We don't have the room. This may seem like a fantasy case, but it's not really. We see this quite often where we have a very small groove that we need to measure the bottom of it, and we just don't have the strike length. It's a question that comes up a lot. We could cheat. Quite frankly, we could cheat with a profilometer and we could make a small strike length and ignore the ISO guideline. And as much as I'll generally tell a customer, you know, if ISO doesn't work for you, just make a note on your drawing so you're not adhering to ISO, and here's the reason why, and speak to your customer about it. That's all fine. In this case, there's a reason that ISO provides that guideline. And the point is if you only have a couple of 100 microns of strike length, and you have a fairly large roughness in that area, you need to do more than a half a millimeter or a quarter of a millimeter of strike, have more than a half a millimeter or a quarter millimeter of data, just to be sure that your data really represents what's going on in that groove. So a single half a millimeter long trace with a stylus, I would argue, is probably not the optimal technique for this. The data density is just not high enough for me to be confident that you're really representing that surface. There's absolutely arguments against what I'm saying, but that's what I'm proposing to you right here. The solution to that I am proposing is we use a 3D parameter. The reason being simply just higher data density. We can use, even though we're limited to a half of a millimeter wide, we're still limited to that half a millimeter. We have a lot more information going around the circumference of that, even compared to doing 5 or 6 or 7 stylus traces. We have 2 orders of magnitude more information than that from a single measurement. And my proposal to you is that that is going to give you a lot more of a reliable representation of what's happening in that groove than a 2D measurement. And here we're showing as just, again, a typical measurement that we would use in there, a typical 3D measurement, producing the SA value, which is the 3D equivalent of the RA measurement. but also the SMR, which is again the equivalent of RMR from the Abbott Firestone curve, and the 10-point height here. Also giving some directionality, again, more data that you're not necessarily going to get out of a stylus trace. Directionality in particular going to be important on a surface like this, where you really want to make sure that you do have the correct directionality, right? You're supposed to have you don't want that, it would be impossible to get it anyway, but you don't want the lay of your surface to be going parallel to the axis of that shaft for leakage points on a sealed surface. So there's more information in this tiny little 3D measurement than you're going to get out of this with a 2D measurement, is the point here. So I propose to you, we have to step away from RA. If your customer is calling out or is calling out RA on this drawing where you can't do RA, you're going to have a discussion with the customer about that anyway. You're going to have that discussion. Look, you really can't have that on the drawing, or how do you expect us to do this? You have to have that discussion anyway. You might as well have the discussion of, look, instead of using ISO 4287, let's use ISO 25178 and SA. It's going to give us a better explanation of what's going on this tiny little surface. So you're in for a discussion anyway. You might as well have the right discussion. Get the discussion from 2D RA over to 3D SA. That's my example for these small, difficult to access measurement areas. And now we get to the big one. Looking at the clock, we got a little bit of a late start. I want to make sure we have time to get through this and still give you all an opportunity to ask questions. So let's get right into it. I'll try to go pretty quickly. Inside of ISO 25178, we have these 5 groups of parameters: the amplitude parameters, the functional parameters. There's actually 3 subgroups inside of functional, but the functional parameters, hybrid parameters, spatial parameters, and structure-oriented parameters. And what I'm going to do is I'm going to give you a couple of bullet points for each of one, just a very 30,000-foot view of each of those. And in the cases where it makes sense, I have a couple of nice examples for those. Start off with the amplitude parameters. Quite frankly, the amplitude parameters are very, very similar. The 3D amplitude parameters, these are the SA, the SQ, the SZ, very, very similar to the 2D parameters, the profile parameters of RA-RQ. At the risk of trying to explain something that's difficult to do without a whiteboard or diagrams, I'm going to go for it. The one big difference between, let's stick with RA, because I think everybody has a good idea of what RA is, but I'll explain it in words anyway. RA is we take our profile and we calculate the mean line of that profile. Forget the filtering. We're not going to talk about the filtering, but we have our profile, we calculate the mean line, and then we go through and we calculate the average deviation of every point on our profile from that mean line. We ignore whether it's above or below, just how far away is every data point from our mean line, and we take that average deviation from the mean line. That's all RA is. The filtering is necessary, but in terms of the math, that's all there is. SA is similar, but slightly different. In the case of SA, we don't have a profile, we have an area. So instead of calculating a mean line for each of the profiles in that area, we calculate a mean plane for the entire area, and then we go through every single data point in our area, and we calculate the average deviation from the mean plane. So it's a subtlety, but it actually does make a mathematical difference when we're looking at the parameters. SA is not equal to the average RA of all of the profiles in the surface, right? So there's going to be some difference between the two, but it's a very, very subtle difference. And in most cases, in practice, it makes no real big difference. So they're very, very similar is the point for all of that. The biggest advantage to the aerial parameters is we just have such a big data density. That said, I don't have a bullet point. I should, in full disclosure, there is an advantage to RA as well. If you have a surface where you know there's some directionality and you know which direction that directionality is, rolled sheet is the perfect example of it. If you want to measure transverse to your rolling direction and parallel to your rolling direction and want to keep that quantified, well, you're going to be able to do it a lot better with the RA parameter. And whether you have optical digital data or stylus data, You can do it either way, but for cases like that, RA is better. So there's no saying one's better or than the other. They're just better. One's better for different applications. I'm not going to give any examples for amplitude parameters because it's pretty basic stuff. Everybody knows what RA, RQ, et cetera are. I'm not going to give examples for it. Functional parameters, on the other hand, these are parameters that are based on this Abbott-Firestone bearing area curve. And on the next slide, I'll show you a picture of one of those. Examples of these parameters in 3D and aerial are SPK, SK, SVK, SMR. They are, I have similar here. I meant to edit this out. They're actually mathematically identical. Mathematically, they are identical to RPK, RK, RVK, et cetera. Exact same math used to get them. The only difference is we are, again, the same bullet point. When we create this Abbott-Firestone curve from 3D data, there's a lot more data that we're using. 2 orders of magnitude more data that we're using minimum. In addition to those parameters, the parameters that are present in the 2D space, the RPK, the RK, and RVK, et cetera, there's also another set of parameters, and those are the volume parameters. I'm going to talk about those on the next page here. So these parameters, they're the V parameters. They are also based on the Abbott-Firestone curve, which I'm showing here. If anybody has questions about what the Abbott-Firestone curve is, we can talk about that afterwards. But briefly, what the Abbott-Firestone curve says is at top, the y-axis is 0%. So the x-axis is percent. The y-axis is our height, our cut height, as we call it. And it starts at the highest height. And what it says is that our very highest point that we have in our data set, 0% of the data is above that data point. And we keep going through for all of the heights, all the way until we get down to the deepest point in our entire data set. And we know that 100% of our data is above that. Another way of saying that is this is actually the integral of our height distribution, is what this curve really is. That's all math. It doesn't make much sense. Generally, it is difficult to make much sense of it. We can look at it a different way, and we can say this little tail up here, this is our asperities. This is our asperities, this flat part in the middle, this is where we have contact. And this area down here, this is where we have voids. This is where we have openings in the surface. That's what this chart represents. These ISO 25178 parameters that we get off of this chart, you could certainly get it off of a 2D data set. You could certainly get the VMP and these, and I'll explain what they are in a second, but you can certainly get these off of an Abbott-Firestone curve from a 2D data set, from a profile, but they do not have the correct meaning. In the case of an Abbott-Firestone curve from a 3D data set, we can say that these represent a volume of material on the surface. If we're taking these data off of a 2D, an Abbott-Firestone curve that looks exactly the same, but it's from a 2D data set, we could calculate this, but we cannot call them volumes because we don't have a volume information. We have cross-sectional area information. So it's a subtle but very, very important difference. It looks very similar, but it's not, is I guess the point. VMP, this is volume of material of peaks. So this is really the volume of asperities that we have on this surface. This is, when we have run-in or burnishing, these are the first materials that are going to be removed. And we can quantify that very, very well with this parameter. On the absolute opposite side, I'm going to jump down to the other curve here. On the other side, it's easier to see, it's much bigger. This is VVV, volume of the voids in the voids. But this is where we are going to collect. This is where we are going to collect any debris from the surface. Even when we burnish or run the surface in, this is where the debris is going to collect. It's also, in some cases, the volume that we have to carry lubricant, or in the case of printing or painting, this is the volume that we have to fill to even get up to the main surface. So it has different meanings for different processes, but we can start to look at this and say, oh, I can actually look at these parameters and understand what the mechanism is between what my surface looks like and how paintable my surface is, or what my surface looks like and how much lubrication I have to put on the thing when I'm deep drawing it. So we can really start drawing concrete relationships back and forth between the mechanisms with these new parameters. That was a lot of information there about a big set of parameters. This is there's a webinar just in this Abbott Firestone curve. There's a webinar or two. If you do have any questions, feel free to fire away at the end. Hybrid parameters. If you remember back to amplitude parameters, I said that those were parameters that are only calculated based on surface height. Hybrid parameters, these are calculated based on height and length. And when I say length, I'm talking about length in the XY direction. Most obvious of these is, would be slope. You can't calculate slope without an XY component. RDQ does exist, so there is a 2D version. SDR is probably the more important of the two. This is the developed area ratio. Can't really do that in 2D. So what this does is it tells you, how much area, how much total contact area. So when we're on an angle, when we're looking at some angled pitch, there's also some area on that pitch. If you think of climbing a mountain, even though the peak may only be in a straight line 100 meters away, but you've got to climb, you've got to walk 500 meters to get to that. This is the quantification of that. How peaky, how slopey, how faceted is the surface? That's what SDR quantifies. And that really plays a very, very important role in tribology, surface tensions, paintability, even conductivity as well. So that's a very important parameter for that. But that's probably the key hybrid parameter there. Spatial parameters, these relate to how repeatable. There's a lot of mathematics in here. I'm not going to get into it, but how repeatable are features in the XY plane. So if we have those back to grinding marks, this is another way of correlating grinding marks. How far on average do we have in terms of spacing between the grinding marks? Or if we have interrupted grinding or check type of marks, what is the, how large is that texture of those grinding marks relative to the transverse direction? So that's what the texture aspect ratio would be. And then of course, STD, there's more than these, but these are the important three. What's the direction of my texture? And the nice thing about a 3D data set is we can pull that out. And I'll talk about that a little bit here. A couple of interesting case studies. I know we're running a little short on time, but I really do want to get through these. On the left side, we have an isotropic surface. We look at that surface, we say, aha, that's what he means by isotropic. I really can't see one direction really standing out as having any lay. I really can't see any lay in that. Indeed. But then we let the mathematics run, and we say, you know what? It's actually not. 70% is pretty isotropic, but there is some directionality to it. The machine does pick out, it does pick out a decent size that it's not a big directionality, but it is able to say that, look, at 115 degrees, there is some larger signal. And then we go back and we look at the graphic up here, and we look at it and say, you know what, maybe there is something there. Maybe there is something in this 125, 115. I can kind of see that. When I run my cursor in this direction, yeah, it does look different than when I think about looking in this direction. I may not have picked that out. That's why we have these calculations, to give us some insight and keep us on the straight and narrow in terms of our qualitative analyses. We can actually, speaking that way, we can turn it from a qualitative analysis where we look at it and say, yeah, it looks pretty uniform too. Oh, well, yes, it's relatively uniform, but it's only 70% uniform. So that's a nice example there. In the middle, yes, we have a clearly anisotropic surface. I look at this surface and I say, yeah, I see honing marks. I see it in two directions. It looks, there's a couple of big ones from the northwest to the southeast. There seems to be some big ones, but by and large, it looks pretty balanced. And that's what the parameters are for. I look down there, and that's what this STR, this texture aspect ratio in English, that's what that's about. If that were 1, it means that there is no aspect to the texture. It's even in all directions. Not necessarily isotropic, but the texture directions we find are even. But here it says no, actually. You know what? Indeed, those northwest to southeast honing marks, those are actually a stronger signal than the southwest to northeast. So these honing marks do give us a stronger signal than these honing marks. And some of you in the audience may say, oh, no, I can see that, Chris. And I would argue back, I don't really see it. But, you know, we can go back to the number and we can say, you know what, quantitatively speaking, there's no arguing with the mathematics. It is stronger. So, and we can quantify that now. And it takes a lot of the human factor and the human judgment out of that. And that's very important. And then finally, this is a really challenging surface. So this is a fairly isotropic surface with some underlying waviness to it. And when I look at this surface, I say, oh yeah, it is pretty isotropic, but boy, that waviness is pretty strong. The interesting thing to see is, in this case, what the mathematics are telling us, at least what it's telling me, is even though we see it, and even in the Fourier transform, we can see it pretty well, there's actually not much waviness there. That waviness doesn't have a very big effect on how our surface performs. And the reason I say that is, first of all, our isotropy is very, very high, but the two things key me in there are our texture. Our aspect ratio of the texture is actually quite high. It's higher than the surface the surface over here that I called the isotropic surface. It's actually higher than that, meaning that the isotropy signal is even lower. So the waviness isn't really having much effect on the isotropy at all. It's a very, very even signal, the directional signals. And then finally, the STD, you have to scratch your head about it for a second, but 81 degrees, 81 degrees is, roughly this direction. That's the direction it's saying it's detecting some texture. And quite frankly, as much as I stare at that, I really don't see it. So it's a very, very weak signal, first of all, and it's not, it's not perpendicular to the direction of the waves, but it's saying there's some signal here, and I really don't see it. So our qualitative impressions say, oh yeah, there's going to be a signal at like 30 degrees. We're going to see a 30-degree signal, and it's it's going to be a pretty isotropic surface, or an anisotropic surface, but it's not. In mathematically speaking, it's really not. So there's a lot to be seen in these parameters here. Final parameter grouping are structure-oriented parameters. These are based on, in a nutshell, fundamentally identifying hills and dales on our surface, or as well as some edge detection and thresholding. So it's looking for individual features and automatically identifying and isolating them so that we can analyze them. We use this, again, peaks, holes, valleys, troughs, steps, etc. So some type of geometric feature that we have a lot of them, and we'd like to identify them somewhat automatically, somewhat automatedly. And this was the example. I'm not going to spend too much time here, but this is what we use to identify these depressions, these pores we refer to, identify these and separate them out so that we can classify and quantify the pores, and then also classify and quantify the surface without the pores. So that's when we would use these this type of parameter set. So I guess I actually thought I had another slide after that. There should be a slide after that, but we'll use the black slide. This is the point where I'd say, if there are any questions, this is a great time to field some questions. Lori, if you can help me with that. But I thank you for your patience and your attention. I spoke very quickly to make sure I stayed close to 45 minutes after the slow start. I'll see if I can get the slide up that actually I wanted to show so we can, there we go. So there we go, there's my email address. So if you have, or it's not my email address, but anyway, if you have any questions, I think you all have Lori's email address. You can reach out with questions. Lori, do you see any questions in the comment section there?
I do not right now.
Okay, all right. Again, thank you everybody for your time today. Patience. Feel free to reach out. I'll stick around for a minute or two in case any questions do come up. Feel free. Again, thank you very much.